Hello friends, today we will learn a new topic of chapter number 4, and that is force between two parallel currents and definition of 1 ampere, which is defined in SI system. So first of all, the force between two parallel currents. Now here we are learning that magnetic effect for current. That means when current will pass through any conductor, it will produce magnetic field, and obviously in this field some force will exert on the region around it. So now first of all, what we know, that basic understanding that we already have, that we will put over here, that we know that what we know in physics we write many times that we know that, but ultimately we must know that. So what we know over here, so we know that force is equals to I L cross B. Now this is the equation of magnetic force, and it is given by the condition when in the wire I current is passing through it. If we consider a small element length L into that conductor, and if that wire is kept in a magnetic field, then it will experience force around it, and that equation is given by the equation number 1 that I am writing over here. Now the question is here, that is force between two parallel currents. That means what we need, that we need to draw two parallel current carrying conductors, say wires. Okay, so here first we will draw two conductors. Say I draw one wire is with blue color pen and another wire which is parallel to it with green color pen. So here it is very clear, I can say that one wire, that is said to be a wire A, and another wire that I will call it as a B. Now the current that will pass through the wire A will be I into suffix A, while the current through wire B, that will be IB. Now it is clear that these two wires are parallel to each other, and say there is a distance D in between them. So now we say that these two parallel current carrying wires or current carrying segments are kept parallel to each other. Now we have to find out that how much force that will be exerted between A and B due to that current and the magnetic field that will produce over here. Now as per as our equation number 1, what we will do here, first of all I will take a small segment of length L. Say I will take a small length L into this wire. Say this I have taken as a very small length L. I represent it here with capital L, this length. Obviously the current is indicated as it is flowing in the direction. Now here we are considering that the magnetic field is given in this case as the downward direction as shown in the figure. So I am showing that this is the part that is magnetic field which we have already set up, and the magnetic field is acting in downward direction due to wire A. So here I set up it in this manner. It is not like that always, but in this case we consider it, and due to that the force acting on wire B due to A is given by FBA. So in textbook they have shown this part. now how to understand it, that we will go step by step. So first of all we will focus on the figure and our equation number 1. Now we know that if we are given a long current carrying conductor, that means here we consider two wires are of long dimension. Here long wire means what? Again, long wire means their length is comparatively very large with respect to the radius of their cross section. So here wire A and wire B are considered two parallel long wires. Now the magnetic field due to wire A on wire B is given by, or we say that not exactly on wire B, but first of all we will say that the magnetic field due to A at distance D from wire A is given by, that is mu 0 IA, where IA is a current passing through wire A, upon 2 pi r, but here the distance that I am considering is a D, and therefore the magnetic field is given as a BA. So this will be my equation number 2. Now what we are doing, now we are taking wire number B and we consider a small current carrying segment, that is L. So as we have shown in the figure, we consider that the force acting on B due to A, that I can say that therefore force acting on B due to A is written by, that is IL cross B, but here I that will be of wire B, length also will be of wire B, and IL that B will be of wire A. So magnetic field will be of wire A, while the small current carrying segment that we have considered is from wire B. So this IL part will be from wire B and the magnetic field will be from wire A. So when we combine it, we get, when we replace it with the value of equation 2, we can get mu 0 into IA into IB into L over 2 pi D. So this will be our equation of force. Now exactly as per as Newton's law or Coulomb's law, we can say that whatever force is exerted by wire A on wire B, the same force will be exerted by wire B on wire A. Here also it is very clear that the direction of forces will also be the opposite. So if FBA that we have shown, that is moving from B to A, okay, that is indicated by B to A, in the same manner if we say that FAB would be there, then it will be from A to B. So we can also apply that Newton's law. It is just like Newton's law, it is not a Newton's law, and then we can say that here, that is if we say that FBA is from wire B to wire A, then FAB would be from wire A to wire B, and in that reference we can simply state that FBA, if indicated in a vector form, it will be minus FAB, and that is nothing but Newton's third law of motion. So here it is just like third law. We have indicated it with equation number 4. Here we can say that this is consistent with Newton's third law, and thus at least for a parallel conductors and steady currents, we have shown that the Biot-Savart and Lorentz force yield results in accordance with Newton's third law. So here we have applied Biot-Savart's law and Lorentz force. Biot-Savart's law in the terms to find out the magnetic field, and force in the terms IL cross B. So they brings us the result like Newton's third law. Now the interesting thing, that one more comparison is there, and that indicates that if the currents are in the same direction from the wire, they will attract each other, and at the same time if the current are in the opposite direction, then they will repel each other. So here for the current terms of view, we can say that parallel currents attract. So we simply state that parallel current attracts, while anti-parallel currents repels. But we have to remember that this part is actually the opposite to the Coulomb's law. Now here we will see that how it is that. So if we compare it with Coulomb's law, it shows contradiction with Coulomb's law. How that contradiction with Coulomb's law, and that is like charges repels and unlike charges attracts. So it is opposite to this electrostatics or the Coulomb's law. But here this part is important for the understanding point of view, and therefore we must remember this portion as our general knowledge part. So here this portion that we will keep in our mind for the exam point of view, which is useful for the examination purpose, and we will keep it in our mind. Now one more thing that we can apply, that generally this force with a long wire length, we generally use it in a term that is, we can say here that force per unit length. So if I write the equation as FBA, this would be nothing but FBA over L. So that L term will goes to the denominator from this equation number 3. So if we take this L to the denominator, we will have now an equation that is equals to mu 0 IA into IB over 2 pi d, and this is called force per unit length. So force per unit length in condition that is given over here, it is very clear that this expression is used to define the ampere. So now from this equation we can define the SI unit for current electricity or for current, that is ampere. It is given that the ampere is the value of the steady current which, when maintained in each of the two very long straight parallel conductors of negligible cross section. देखो यहाँ पर हमें ये कंडीशन लिखना बहुत ज़रूरी है, that is two conductors must be of a very large length and they are having a very negligible cross section and placed 1 meter apart in vacuum. So if we are taking different values from this equation, if I say I take some different values like D is equals to 1 meter, I am taking over here, suppose D is equals to 1 meter, then if I say these two wires are very long, they are straight, they are parallel and having negligible cross section, then if we put them 1 meter apart in vacuum, and that would produce on each of these conductors a force that will equals to that, if we put all the values as a unit, we found that force to be 2 into 10 raised to minus 7 newtons. So if it produces this much force per meter of length, so this much force per meter, then this current is called 1 ampere. So again, what is the definition of ampere? I am repeating that the ampere is the value of that steady current which, when maintained in each of the two very long straight parallel conductors. So I would like to differentiate and separate all the terms, that the ampere is, we will take one to one word, that the ampere is the value of that steady current. So is the value of that steady current which, ये कौन से करंट की बात है, that means which when maintained in each of the two each of the two. Which two? So we say that it is very long, then straight, then parallel conductors, parallel conductors. Of negligible cross section. So we have to keep them of negligible cross section and placed 1 meter apart. In vacuum. That is the basic condition, that we have to put it in a vacuum. Would, what it would produce? So when we put it in a vacuum, मैं इसको ब्रैकेट में लिख रहा हूँ, we need not to write it. It would produce on each of these conductors a force which is equals to 2 into 10 raised to minus 7 Newton per meter. So this force would be in the term of newtons per meter of length. It would be called an ampere. So this is the definition of SI unit of current, that is ampere. So from the above equation, again we can simply explain that what is ampere. So from that above equation, that is force per unit length, if we are considering everything to be a unit value, then with certain condition we can have the definition of ampere, which is actually force per unit length. So again I am repeating the definition of ampere. Please have focus over here. It is given that the ampere is the value of that steady current which, when maintained in each of the two very long, यहाँ पर देखिए ये कंडीशन उन्होंने अप्लाई किया है स्पेशल, very long straight and parallel conductors of negligible cross section. This is the basic condition, that these are the characteristics of the wire, that this wire must be very long, they must be straight, they must be parallel to each other, then and only then this equation is valid, and they must have negligible cross section with respect to their length when they are put 1 meter apart. That means in the above equation, if d is equals to 1 meter, and if we put all that value, we will get the value of force that is equals to, that is about 2 into 10 raised to minus 7 Newton per meter of its length. Then the current that would be passed through that wires would be 1 ampere. So this is the condition and the definition of 1 ampere, which is SI unit, and this is defined as per this statement. When a steady current of 1 ampere is set up in a conductor, the quantity of charge that flows through the cross section in 1 second, that will be also 1 coulomb. That is also Q equals to IT, that we have already defined earlier in our segment of the textbook. Now it is given that the horizontal component of Earth's magnetic field at a certain place is 3 into 10 raised to minus 5 Tesla. So we are given the value of B H, that is 3 into 10 raised to minus 5 Tesla. This is the value of magnetic field is given, and the direction of the field is from the geographic south to the geographic north. So here in the figure I have shown that the blue color is a part of Earth, while the magnetic field inside the Earth that is given, that is from geographical south to the geographical north. Now a very long straight conductor is carrying a steady current of 1 ampere. So here we are also consider the next part of the information. Suppose this black color that is lying on the table is this stated long wire. So a very long straight conductor is carrying a steady current of 1 ampere, and here the value of current is given as a 1 ampere. So of 1 ampere current it is lying, what is the force per unit length on it? That means we have to be careful that here the wire has a very long length, and therefore its length is not to be considered, and therefore the force per unit length that we have to calculate. So what is the force per unit length on it when it is placed on a horizontal table? Here it is given that horizontal table, we have to consider that it is a very long. So on a horizontal table, and the direction of current is, this is the first case that I have noted as 1, and that is east to west. So if the direction of current is from east to west, we can simply apply the equation that F is equals to IL cross B. We can say simply that F is equals to IL cross B. Here length of the wire and magnetic field are perpendicular to each other. Here it is clear that magnetic field B is in this direction, while current is flowing in this left hand direction, and they are having 90 degree in between them. So here that theta will be 90, so the cross product will have the simple term, therefore the F will be as ILB. Here length is already given, that is very much large, and therefore we say that in this case this would be force per length, that is small f, and that is equals to I into B. Now we are given the value of I and we are given the value of B. So on the basis of that, this F, that is small f, will come out to be 3 into 10 raised to minus 5 Newton per meter, because this is force per unit length. Now we are also asked to find out the direction. So the direction will be from this above equation, that is called the right hand screw rule. So if we apply that right hand screw rule for this portion, we can have the direction of the resultant force. So here, from this condition, the direction of force with a right hand screw rule, if we put right hand screw over here on this part and we move it on this path, it will move inside, so that the direction of force is inside the plane. So it is moving inside. So the direction of force is inside, and here in this case we can say that from our part it is upward to downward. So inside of plane. So this is about the force and the direction of that force. This value of force is very large, and practically when we say that, it is very larger than even 2 into 10 raised to minus 7 Newton per meter. So this value of the force is for the Ampere definition, and therefore it is important to eliminate the effect of Earth's magnetic field and other steady field while standardizing the Ampere value. So when we are defining Ampere value, so all these Earth magnetic field and all these values should be eliminated or should be neglected. Now the second question is also asked in the information. They have asked that if the direction of current is from south to north, then what will happen? Then also we have the answer that here the magnetic field is already in the upward direction. It is clear that magnetic field is already in upward direction, and the current is also moving here in upward direction. So for us, it will be easy part for us, that we can say that current I is flowing here, and at the same time magnetic field is also in the same direction, and therefore they are parallel to each other. So I is parallel to B, and therefore theta is 0, and therefore it will exert no force. So force would be 0 in the second case. So if we are given these two cases, we can say that in first case the force will act inside the plane, while in the second case there will be no force act all, because they are parallel to each other. So this is the information and the application of Ampere circuital law. We can say that Lorentz law we have applied overall, that is Biot-Savart's law, and that is the combination of all the magnetic effects. This is example number 4.10.